Yeah, my PowerPoint slides don't seem to be able to load, and the computer is slowed down. Okay, all right, let's get started. Okay, so this morning we will go into topic 3, exponential and logarithmic function, which in your degree programs, in your modules, when you come into SIT to study, you will definitely come across all these exponential and logarithmic functions, definitely. Okay, so right, so let's go to the next slide. Okay, give me a moment. All right, so for exponential functions, so when you have x to the power of something, that definitely is a exponential function. So m, for example, x to the power of m over n. So m over n is called an exponent, or we normally call power, x to the power of something, or exponent. And x to the power of m over n can be written as n root of x to the power of m. Okay, and it can also be rewritten as this: root n of x bracket m. Right? And notice also that x to the power of minus p can be rewritten as 1 over x to the power of p. And bracket xy, bracket to the power of p is x to the power of p times y to the power of p. And xy, holding bracket, to the power of p is x to the power of p over y to the power of p. Okay? So note all this, different ways of writing the same thing. All right, these are all exponential function. Okay, and when you have x to the power of p bracket to the power of q, then it's x to the power of p times q. Okay, but when you have x to the power of p times x to the power of q, then it's x to the power of p plus q. And then you have this division: x to the power of p over x to the power of q is x to the power of p minus q. I hope I'm refreshing your memory. Okay, so it is very important that your when you have x to the power of p times y to the power of q, that is not the same as xy to the power of p plus q. Okay, so because this has to be the same. Okay, so equipped with all this, let's do some examples. So in practice, exponential functions are frequently encountered. For example, what are the things in life that change exponentially in terms of numbers? Okay, so one thing is you can say bacterial growth. Bacterial colonies, they grow. They're allowed to grow. They can grow very fast in numbers. They can grow exponentially. Bacterial colony. If you do it there, the next day they will grow, and the next day they grow very, very fast. And it's exponential growth in bacterial population. Okay? And there are also many examples of exponential functions. Okay, right. So how to convert each of these exponential function? Okay, let's take a look, applying all that we've just been refreshed. All right, so we have 3 times square root of x to the power of 5. So applying what we just learned, okay, that would be equal to 3, constant remains as it is, and x to the power of 5 over 2. Okay, that's the answer. That becomes exponential form because x to the power of 5 over 2. 5 over 2 is the exponent. Okay, B. 5 over cube root of x. Okay, so the answer would be 5 stays as it is. Then you must bring the cube root to the power of x, root x up, x to the power of minus 1/3. Okay, and C, okay, you have this term here, 3x squared over 2 root x. So C, that the next step would be your 3 over 2 is a constant, so we don't touch the constant. And and then we keep the x squared in the numerator, okay? And the 2 root x, it can be rewritten x to the power of half, okay? To the power of half. So that can be further rewritten as 3/2 x to the power of, now you're going to bring the x to the power of half up, becomes x to the power of minus half. So x squared minus half, okay, using the what we have just been refreshed, and then you simply get a final answer, x to the power of 3/2, okay, into the final exponential form. So A, B, C, and D, you have 2 to the power x times 2 to the power 3 plus x, opening bracket, square. All right. So for D, you can rewrite that. So that would be applying what we have just been refreshed. There will be 2, because x, you can add x and 3x and 3 plus x together. So it will be 2 to the power x plus 3 plus x. Okay, square. And you continue, and that will be, you have x plus 3 plus x. So it's 2 to the power of 2x plus 3. Holding square. And then you can then arrive at the final answer. You multiply the square into your 2x plus 3. So it's 2 to the power of 4x plus 6. Okay, so that is the final exponential form. All right. Okay. Any questions so far? No? Okay, good. So let's continue. So graphs, let's look at some of the graphs of exponential function. Okay. For example, how is a graph of let's say the following exponential function? How do they look like? Okay, you have E, this E here, you'll come across it. E is called Euler's constant, and it's a constant. There's a number there, 2.7182818. Okay, Euler's constant. It's used commonly as a natural logarithm. All right, let's look at some of the graphs, how they look like there. So y is equal to 2 to the power of x. It's an exponential function. The exponent is x, and 2 is called a base. Okay, so the graph looks like what is shown there. So it grows exponentially as x increases. All right. So if we were to plot this is how it will look like. Okay. And if you plot y is equals e to the power of x, another exponential function, this is how it will look like. Quite similar, but not exactly the same, simply because e is very close to 2. It's 2.718, 2.23 decimal places, okay, to the power of x. So it's close to the one on the left, 2. So they look same, rising up exponentially, but of course not exactly the same curve. Okay. Now, then what about y is equals half to the power of x? That's how it looks like. Okay. The base is 1/2 instead of 2. So it goes this way if you plot it out. Okay. Then what about graph of y is equals e to the power of minus x? How does it look like? What do you think? Y is equals e to the power of minus x on the right side. Of course, if you were to sketch it out, normally you would just put in some values. Okay, put in some values. Okay, you have a x column, y column, and you're working, if you like, working the result. So that's your, and then continue. For example, when x is equal to 1, what will y be? Then you just have to continue from there. Okay, when x is here, you just work from there, whatever answer is here, whatever answer is. You can do a working here if you like. If not, you can leave out this. Can x is 1, x is 2. You can start with x is 0 if you like. Then you will to do a plot of this. of this graph. And it should look, it should look, let me see where I got it. Oops. Okay, it would look something similar to the one on the left. I just do a sketch, just do a sketch, something like that. Just do a sketch, okay? It will look something like that. Okay, because just like before, y equals e to the power minus x is the plot should be quite similar to the one on the left, because y equals to half the power of x is 2 to the power of minus x. Okay, 2 to the power minus x. And your e here is close to 2 because it's 2.718. So it will look similar, but not exactly the same. Okay, so these are called, these are exponential functions. Exponential function. All right, next, just close this. Okay, next, usefulness of exponential function knowledge. Okay, just an example, the usefulness. Okay, many relationships between variables in nature are linear, some are non-linear, okay, some are exponential, or in a power form, some are exponential. So let's say in an experiment, you obtain measured data, and your measured data is shown. For example, when x is 1, you measure y is 3.3. When x is 4, you measure y in your experiment. Y is 23.3. And then when x is 10, 82.9, and so on. So you, from experiment, you got a table like this. Okay. And then when you plot this table out, when you plot this table out, you get this exponential curve. So you can see, by now can recognize this is the exponential curve of the order y is equals to a x to the power n. Okay. Now, so when you got a set of data from your experiment, you got a exponential curve like this of the form, you know, is y over a x to the power n. What can you say? Any meaningful information can you obtain from your exponential plot? Normally, researchers want to find out what is a, what's the value of a for this curve or exponential curve, and what's the value of n. Two important information researchers want to find out. But with a curve like this, how can you find a and n values? What do you think? How can you find the a and n values? Yes, this is your x-axis, and there is your y-axis. Oops. Very sensitive, this. Okay, and that is your y, So how can you find the values of a and n? So the way the researchers would do is to resort to a logarithmic plot using a logarithmic versus logarithmic scale graph paper, which is what you see here, the gray paper here. Okay, this is what you see. This is called a log, means y is log scale, x-axis also log scale, is a log graph paper. I wonder how many of you have seen the log, okay? So, so with the same data as you see here, same as what you see over here, it's the same data. Now we're going to plot it on the log graph paper. The axis, vertical axis is as usual your y, and horizontal axis is as usual your x. Okay. So the graph paper, the scale, how do you understand the scale? The scales are the grid is very different from your ordinary graph paper. So the grids for log graph paper, they are not of equal spacing. Okay, as you go from, for example, 10 to the power of 0 to 10 to the power of 1, you see the grid line, the spacing gets smaller and smaller. So one box here, a jump is times 10. So the next from 10 to the power of 1 to 10 to the power of 2 is another box. Okay, and then 10 to the power of 2, and 10 to the power of 3, 10 to the power of 4. So from 10 to the power of 0 to 10 to the power of 1 is is called one cycle. 10 to the power 1, 10 to the power 2 is called another cycle. So this is a 4x3 cycle log graph paper. 4 on the y-axis, okay, 4 cycle on the y-axis, and 3 cycle on the x-axis. So this is a 4x3 log graph paper. So now back to the the gray color log graph paper. Huh? So you plot your data onto this log graph paper. Okay, so for example, when x is 1, so this is 1, huh? This is 1. This is 2, 3, 4, 5, all the way to 10. So when x is 1, which is here, what's your y value? Y value is 3.3. So 3.3 is somewhere there. X is 1, y is 1, y is 2, y is 3.3. When x is 2, which is here, x is 2, you go draw a line there, and then what's your y value? Is 8.7. This is about 8.7. And then so on and so forth. You plot. Then you realize, wow, by so doing, you have converted a curve that is plotted an ordinary graph paper into a straight line on the log graph paper. And straight lines are easiest to evaluate. So in such cases, what you do is you will then be able to find what is A and what is N. Let's say you take this point here, this is your point 2. And you take this point here, it's your point 1 and point 2. Okay. And here you can take the slope. You can take the slope. Okay, I don't have the space here, so I would use the visualizer, be clearer. Let me go to visualizer. I hope the black screen won't pop up regularly again. So in this case, you know that your relationship you obtain is a exponential function. So you want to find A and find N. Now, later on you learn, you can take the log of both sides. Log y is equals to log A x to the power of N. Take log of both sides. And later on you learn you can actually expand this. Log of A times x to the power of N can be expanded to log A plus log x to the power of N. Okay. This can be rewritten as log A plus, you can bring the N to the front. This is another rule of logarithm. Later you learn. N log x. So now you have log y is equals to log A plus N log x. If you look at this, this is similar to what you have learned in your school days. Y is equals to M x plus C. Equation of a straight line that has got a y-intercept is equals to log A plus 0. So if you look at this, therefore y is equals to A. So if you look at your gray log plot, graph plot, okay, when x equal to 1, what's your y value? Y value on the graph is equal to your A. And on your plot is 3.3 from graph. So you got your A already. So your A is what? 3.3. Okay, your A is 3.3. You got one value. That's very good. You found A already, you see? Very useful information. Okay. So now, what's your N? So from here, N is actually the slope of your straight line on your log graph paper. So slope of log plot, we call it, is your N. So from your graph, is log of y2 minus log of y1 over log of x2 minus log of x1. It's just taking the x1, taking the slope from your log graph paper. Okay, so if you look at your log graph paper, you just have to see that at point 2, what's the y2 value? At point 2, what's the y2? Y2 is about 40, 40? 40.5 log of 40.5 minus log y1. What's the y1? At point 1, what's the y value? 8.7, about 8.7. Similarly, you look at the x value at point 2. What's the x value? At point 2. It's about 6. And the x value at point 1 is log of 2, about 2. X value is about 2. So use your calculator, you get 1.39, which is approximately 1.4. So there you are. By doing a simple conversion from an ordinary graph plot to a log-log graph plot and understanding your logarithm process, the steps, you can find that from your measured set of data, the equation of that curve is y is equals to 3.3 x to the power of 1.4. There you are. Very useful data coming out from there. Okay.
Hi, so can you go through how you got A again?
From here, these steps, you got log y is equals log A plus n log A. You will learn this in a moment. Okay, never mind. Okay, so this is in the form of y is equal to c plus mx. Okay, this is y is equal to c plus, this is your m is your n, x. Equation of a straight line. Remember, this, okay, from your school days, secondary school, whatever. Okay, equation of a straight line. Y is equals to mx plus c, remember? This is your x, this is your y, and this is your intercept, c, okay? This is your c, okay? So this is of this, so on a log graph paper, it is of this form, of this form. So from here, I can easily get value of y first. So I put when x is equal to 1. So here your x is equal to 1. Remember, from your log graph paper, then you go to 2, 3, 4, then go to 10. So, and when x equals to 1, that's where it cuts your y-axis. When x is equals to 1, okay, 1, log 1 is 0. This whole term disappears. So log y equal to log a. Log y equal to log a when x equal to 1. Therefore, now remove the log on both sides. Y is equals to a, 3.3. Your y value becomes your a value. Y equals to a. Okay. So a is what? Is your c, you see? Is your intercept value. Okay, which is, in this case, from your log graph paper is 3.3. Okay. All right. So these are some of the fundamentals, basic use of a log graph paper and understanding logarithmic function. Okay. All right. If you don't understand, slowly you will go through it one more time. You'll come back. Things will become clearer. All right. Let's go on first to the next one. Okay. Now, so logarithm. Okay. That's not exponential. Now it's logarithm. So I've used the example using log, because exponential and log are related, you see. One another, related. Exponential convert to log to exponential. They are related, you see. So, okay. So this is a log function. Y is equals log to base b of x. Okay. Can be rewritten as x is equals to b to the power of y. This some of the rules of logarithm, the rules. Okay, if you like, the rules. All right. And log, this is called long, natural logarithm, ln, natural logarithm, is to base e. Okay, there. Oops. Oh, this happened again. I don't know why. Okay, so there, log e or long e. Okay, log to base e or long e, natural logarithm. Okay, is to base e. So long of e to the power x.
Your screen not showing.
Is it? Oh, okay, give me a moment. Huh? I don't know why. Wait a minute. Huh? Okay, let me close this. Okay. Suddenly my Zoom disappears. Okay, suddenly my Zoom just closes, you know, I don't know why. That's why, was it this one? No, not this one. This is the URL. See, comes back. Okay, share. Okay, can you see? Can see, yeah? Okay, all right. Okay, I can see, yeah? Okay, so long e to the power of x is equals to x. So just like many other things in mathematics, there are rules, okay? Rules. So long e to the power of x is equals to x for any x, and e to the power long x is x. Okay. So just now during the showing you the graph, I've used this rule: log x to the power n is equals to n log x. It means you can bring the n to the front of the log. Okay, this is another rule. Log x to the power n can be rewritten as n log x. So that means long to the power of xn, long of an exponential function, long to the x to the power of n can be rewritten as n long x. You can bring the n to here. It's just like here. Okay. So these are the rule. Common logarithm and natural logarithm are different. Common logarithm means log to base 10. It's called common. Commonly used logarithms, log to base 10. Okay. Natural logarithm is log to base e. Log to base e. Okay. All right. Okay. All right. Evaluating logarithm. All right. We know that log to base 10, so it's a common logarithm. Log to base 10 of 10 is 1. You can use a calculator, you know. Log 10, give you 1. So log to base 10 of what give you 2? Will be log to base 10 of 100. You can check with the calculator easily. Yeah? And log to base 10 of 1,000 would be 3. Okay, you can use always can use calculator to check. Okay, so very common people will use log to base 10, which can be also represented as log 10. Sometimes they just remove the subscript 10, assuming that you know when you put log 10, it's common logarithm. But this natural logarithm, they have to be very specific. Make sure they will put the e there, or if not, they put ln, long. Okay, long, right? Natural logarithm. Okay, all right. Do a simple example without using a calculator, because this is log to base 10. Calculator have it, but without using a calculator, from what you have just learned, find the value of log to base 10 of 110. Now, can you try? You have a go? Have a go at it. Short answer, very short answer.
-1.
-1, is it? -1, is it? Answer, okay. What about the rest? I mean, use calculator, sure, we give you the answer. But let's say if you don't use calculator. Okay, here, let's do it here, since there's some space here. Okay. Log 10 of 1 over 10. Okay, applying what we have learned is log to base 10. Okay, and so 1 over 10 is actually 10 to the power of -1. Okay, and now this -1 is like n, you see, so we can bring it to the front of the log. So so it's -1, okay, times log to base 10 of 10. And log to base 10 of 10 is 1. -1 times 1. So we get -1. Answer. Okay, that's good. Well, next one. B, long of e cubed. Long of e cubed. This simply use what we have just learned. You can bring the 3. In front of the long. So it's 3 long e. Okay, let me just rewrite this. 3 log to base e of e. So when log to base e of e, as what you have seen here, log to base 10 of 10 is equal to 1. So log to base e of e is also equal to 1. So it's equal to 3 times 1, and the answer is 3. Without using the calculator. Right, next. Okay, next. So solve the equation. Solve the equation long x plus 5 is equals 3. Solve for x. Solve, that means find the value of x. And b is, again, solve the equation. E to the power x plus 4 is equals to 7. Solve for x means find the value of x. And the answers are there. Answers are there. So how do we do that? How do you do that? Okay, so for A, there's some space here. I'll write it here. Okay, we're going to apply some of the rules that we just learned. Okay, you have, I'm going to put the 3 on the left. Okay, put the 3 on the left. Okay, I'm going to put it this way. Okay, never mind. For A, I'm going to put it in exponential form. Okay. Okay, let me just put it. Try to solve it as simpler as possible. Right, so long is actually log to base e of x plus 5 equal to 3. Okay. Now, use one of the rules that we have learned just now. You can bring the e to here, and the 3 becomes a power. Okay. So you have therefore x plus 5. Now you bring the e up, and you bring the 3 up. 3 becomes power. Becomes e 3. This is one of the rules that we just learned. E cubed. So therefore, i.e., x is equals to e cubed minus 5. Can use calculator. E is 2.718. Okay, can use calculator and you should get 15.09. Okay, just 2 or 3 steps. You get the answer already. Then for B, you have to find the answer for B. So for B, you can take the natural logarithm of both sides. So you take the natural logarithm of both sides. Long e to the power of x plus 4 equal to long 7. And now we have x plus 4. You can bring it to the front of long, i.e. x plus 4 long e is equals to long 7. Okay? So you know this is log to base e. Log to base e will give you 1. Okay? Log to base e of e will give you 1. So therefore, x plus 4 is equals to long 7. So x is equals to long 7 minus 4. Okay? Then you can solve it in very simple. Use calculator, get minus 2.054. Okay, so a few steps, you can get the answer, 2.054. Okay, using some of the rules of logarithm. Okay, so there are rules that are very used, and there are also some more rules which is shown on the next slide. Okay, and some rules are already shown to you. So log to base b of x times y is log to base b of x plus log to base b of y. Okay, it's a plus. Multiplication is a plus. Then division is a minus. Okay. Then log to base b can be any number. Log to base b of x power y. You can bring the y forward to here. So you get y log to base b of x. We have used some of this already in our solution.
So I can show the previous slide again.
Okay. All right. Now, some more. Okay. Can I go to the next slide? Okay. Next slide. Okay. More examples. Write each as a single logarithm. So you have 2 log. Combine this to become 1. Same. Combine this to become 1. So how do you combine so it become 1? So A, you have log to base 2 of 27 to the power of x minus log to base 2 of 3 to the power of x. So we're going to use rules. So we have A, 27. 27 is actually 3 to the power of 3. We'll try to make these numbers quite the same. So it'll be log to base 2. 27 is 3 cubed to the power of x minus log to base 2 of 3 to the power of x. Okay, so i.e. so you have so you can multiply these 3 and x from our indices earlier yesterday's lecture. So this is 3 to the power of 3x. So 3x you can bring to the front. 3x log to base 2 of 3 minus here same thing, we bring the x to the front of log, so it's x log to base 2 of 3. Okay, so you have 3x of log to base 2 of 3 and minus x log base 2 of 3. So in other words, I put there i.e. Should put equal. So that is equal to 3x minus x give you 2x. 2x log to base 2 of 3. Okay, then you put it back into exponential form, becomes log to base 2 of 3 to the power of 2x. There. Okay, so you have convert these two logarithm terms into just one log term because you write it as a single logarithm. Then B, log 8 minus 3 log half. Log 8 minus 3 log half. Okay, so log 8 minus 3 log half is actually, okay, log 8, again, you try to make the log value the same as before. So, okay, so log 8, 8 and 2. Okay, so 8 is 2 cubed. Okay, 8 is 2 cubed. So log 2 cubed minus, when you have 3 log half, is 3 log 2 is in the denominator. So bring it up becomes 2 to the power of minus 1. Okay, and you continue. As usual, you can bring the 3 to the front of log. So 3 log 2 and minus 3. And again, you can bring the minus 1 in front of the log. So it's minus 1 log 2. Okay, now you just evaluate normally. This will be 3 log 2 plus, because minus 3 times minus 1 is a plus 3 log 2. 3 log 2 plus 3 log 2 plus 3 log 2 is 6 log 2. And now we clean up nicely. Put into exponential form is log 2 to the power of 6. And okay, if you like, I can go to the next step. Where's 2 to the power of 6? Before. So I can put in this form or put in this form is fine. Okay, either form, right? Log 64. Because they are already single logarithm already. So that's how you manipulate logarithm functions which contain exponential functions to find what you want. Next, okay, next. All right. Now, just now we converge into one logarithm from 2 to 1 term. Now you expand, you go the other way. You expand, you go the other way. So how do you expand? To this function. So that function, okay, your log x3 y4 over z5, you want to expand it into various long terms. So you have a numerator and denominator. So log of the numerator, x cubed y4, And Z5 is in a denominator. So when you put a long there, you minus long Z5. And you can further expand it. When you have x cubed and y4 is a plus. So it's long x cubed, and because multiplication is a plus, long y4 minus long z5. Okay, so now we use another rule which you have learned already. You can bring the 3 in front. So 3 long x plus 4 long y minus 5 long z. But if you want to keep it in this form also okay lah. Okay, because you already expanded into 3 logarithmic terms already. This is fine, and this is also fine. Okay, so you may say, well, logarithm, why do all this hard way? We use calculator, just calculator. Even exam and even test, I have log to base e, I have log to base 10. I can use calculator. Why learn all this manual method? Okay, it's not always you will encounter log to base 10 or log to base e. Sometimes you encounter log to base of other values. For example, log to base 2 frequently can encounter in computer engineering because it's binary, binary. Okay, this is here, okay, shown here. Changing the base of log expression. Example, determine log to base 2 of 36. Now, if I say, let me find the value. What's the value of log to base 2 of 36? If I ask you, find the value of log to base 10 of 36, I'm sure you can use calculator. Okay, log 36, answer straight away. In your exam, in your test paper, easy. But if the test paper says, determine log to base 2 of 36, can you use calculator or not? Can you try calculator? Log to base 2 of 36. Try your calculator and see. Cannot, right? Cannot. Okay. What about log to base 20 of 100? Can find the value of this log to base 20 of 100. No? Of 100. Can find? Using calculator, you try. Cannot, right? So then how do you? So that means you have to use your knowledge to do some conversion so that you can use your calculator. Because now you cannot use the calculator directly. You got to convert, right? So that's why it's called change of the base. Yeah. So base is what? Your 2, is the base. Okay, your 20 is the base. Remember what we just learned? Right, give it a formula. Formula log to any base a of x. Okay, you want to find the value of log to base a of x. So you got to change the base so that you can use calculator. So that eventually you can find the value of log to base a of x. So the formula is log to the base that you want so that you can use calculator of x over log to the same base so you can use calculator of a. This A. That is the formula for change of base. Okay, so now let's look at having to find the value of log to base 2 of 36, which you try hard using your calculator and you find that your calculator. Can you use calculator to find log to base 2 of 36? Anybody? Cannot. So let's try to use this formula. You all love formula. Okay, now, so let's do that. Log to base 2 of 36, applying the formula so that we can use calculator. So it would be log, calculators log to base 10 or log to base e. So we want log to base 10. So here also log to base 10, okay, from the formula. And so here will be your 36. And the denominator will be your 2 from the formula, okay? So now you can use your calculator, log to base 10 of 36 and log to base 10 of 2. Calculator, okay, log to base 10 of 36 is calculator is 1.556 and log to base 10 of 2, 0.301. And then you process further. You get 5.1, oops, 5.1, oh dear, 5.1701 as what is shown here. Okay, so by understanding this, understanding the concept, understanding the principles and the steps, you can therefore find your answer to a not so common logarithm, especially in computer and engineering in the digital world. Right? So now, can you find log to base 20 of 100? Okay, you do log to base 20 of 100. See what you get. Using the formula. Have a go. Okay, I give you the answer here. 1.532. Okay, all right. 1.532. All right, you work it out on your own. Should be quite straightforward using the formula. Changing
the
of the
last
base.
digit, I don't think it's 1.532. It should be 1.537.
Yeah, it's okay. It's okay. You see, it depends on how many decimal places you use. Some students use 1.556234589 over 0.30152835. Because here I truncated. So once you do truncate, the number here will be slightly different from your number if you use all the full decimal number of places, one over the other. You understand or not? Okay, so these are all truncation, deviation in the values because of truncation. You see what I mean? So don't worry about 5.170 or 5.169 or 5.171. It's because how many decimal places you use for your division or your multiplication will determine your final answer. All right? So don't have to worry. Okay? Because students usually worry about slightly different error. These different deviations because of the number of decimal places you use for your division, for your calculation. Some use only 2 decimal places, one divided by the other. Some use 10 decimal places. Okay, one divided. So we get a slight deviation answer. You understand or not? So it's okay. It's okay. All right. Any question? Any more questions? If not, we take a 5-minute break. We come back 5 minutes time. Okay? All right. See you later. Differentiation. Differentiation and integration are generally under the name called calculus. Okay? Calculus. So calculus is differentiation and integration. Okay? So in many real-world situations, to solve world problems, you will need to differentiate, you will need to integrate. So if you are engineer, you will definitely have to encounter differentiation. Yes? Yes?
We don't have the slide for this.
You don't have a slide for this? Oh, I see.
You only release until the logarithm one.
Oh, I see. Okay, let me just check and let me just check. Give me a moment. I thought it's available already. Give me a moment. Okay, can you try it out? Try to go to IMS and see whether they are available. Okay, can you try to see whether the materials are available on IMS now? Okay. Oh, that's good. I thought they should be available. Yeah. Okay. Let me just go to here. Where am I doing now? In a moment. Stop sharing. Integration. Can you see the slides? Okay. You can see the slides. All right. So calculus, which is actually in differentiation and integration, encountered very commonly in practice. Okay. All right. Let's look. So just like exponential functions and logarithmic functions, identity, there are various rules that you can apply to solve your problems involving differentiation. Okay, so the first rule we're going to learn is the power rule. Now, if you look at this slide, this is a plot of y versus x. Now, if y is equals to a constant, then it's just a straight line. Y is equals to c, it's a constant. Okay, so when you differentiate, differentiation means getting the slope, getting the gradient of a plot, of a graph. That's differentiation. So when you have a straight horizontal line, what is the slope? The slope is 0 because it's a constant. Y is equal to C is a constant, okay, for straight horizontal line. So therefore the gradient is 0. So that means you differentiate the constant C, the answer will be 0. Okay, the slope is 0. Now, you have another plot of y versus x. And this time, it's a straight line starting from the origin all the way up, such that your plot is y is equal to x. So in other words, if the x value is 1, y value also 1. Okay? If x value is 5, the y value also 5. Okay. So in this case, the equation of this straight line is y is equal to x. Whatever x value is, so will be the y value. So in this case, what is the gradient of this straight line? Will be 1. Okay. So if this is x is 1, your y will be 1. X is 2, your y will be 2. X is 3, y will be 3. So if you can take the gradient. Gradient means you take the slope from here to there. Okay, here, there. So the slope or the gradient is what? This value, your y value, okay, change in y over change in x. So the vertical line is of 1 unit and the horizontal line is of 1 unit, 1 over 1. So it's equals to 1. Okay, so in other words, for this particular plot where y is equals to x, okay, if y is equal to x, then when you differentiate y, so dy dx is equal to 1. Now, the power rule, when it comes to a further, when you have a exponential or a power, you want to differentiate y is equals to a function there, dx of x to the power r. Very difficult, x4. So dy dx, this one you can understand better. Dy dx will be, you bring the 4 to the front, okay, multiply by x and to the power of 4 minus 1. So it's 4x cubed. Okay, so you differentiate x to the power of 4, you get 4x cubed. 4x cubed. Okay, so it's differentiating this using the power rule. So when you differentiate, the power go down by 1, you see. Okay, you have 3 here, and when you differentiate becomes 2, the power. When you have power 4 here, differentiate, become 3. Go by 1. Okay, right, simple example. Differentiate x8, okay, using the power rule, using a power rule. So by the way, you see this is just a function, but you see a prime here, f prime, that means you differentiate, it's a derivative of x. So in other words, dy dx. Okay, we see f prime means it's a differential form of the function f. Okay, so the function of x is x to the power of 8. Okay, so f prime x will be what? Or you can say y is equals to x to the power of 8. So what's dy dx? Dy dx using a power rule, you bring the 8 front here times x to the power of 8 minus 1. So it would be 8 times x to the power of 7. Power rule. Okay, power rule, using power rule. Okay, or this is the same as y is equals to x to the power of 8 dy dx, which is same as f prime x, is equals to 8x 7. Same. Next one, B, this gt means it's a different function. Is equals to t to the power 107. Okay, g is a different function, just any function. So a function of t is equals to t to the power 107. Therefore, g prime t means you get dg dt. Okay, dg dt is equals to power rule 107 t to the power 106. Okay, in other words, it's like dg dt. All right, I'll be like dg function of time over dt. Okay, 107 times t to the power 106. Using power rule, very easy. Okay, the simplest rule is the power rule. Okay, next you can try out all this. A, B, and C. All right, give some time to do A, B, C. Can do? Go ahead and do A, B, C. Okay, quite easy, right? All right. All of you can get the answer. Answers are all there. A, B, and C. C is the easiest, using the power rule, or using power rule. Okay, A, A, all right? A, you have 1 over x to the power of 19, okay? In other words, you maybe you like to put it this way, in a way that you can understand. Is fx lah. This is fx. Okay, fx. I change fx to y, easier for you to understand. So y is equals 1 over x to the power of 19, which is equal to, using what you have learned earlier, on the exponential functions, 1 over x to the power of 19 is x to the power of minus 19. When you bring up to the numerator, it's minus. Okay, so now it's in the power form. Then you differentiate, and then this can be rearranged to minus 19, and now bring the x below to the denominator, x 20. Okay, there. Then b, I put here. Okay, b, y is equal to cube root
Prof,
of x squared. Yes, yes, you have a
Prof,
question?
for question A, right, is it okay if we just leave our answer as negative 19x to the power of negative 20? Or do we have to do
I suppose this is okay. That means it shows that you have done your differentiation correctly lah. But this will look, it'd be nice to have this, but I suppose you will
Right.
get your mark here, and mark is okay. It's okay.
Okay.
Right?
Okay, understood.
All
Thank
right.
you.
So b, y is equals to cube root of x squared. Y is equals cube root of x squared. Okay, so using your indices concept, we learned the first lesson. This can be rewritten as x to the power of 2 over 3. Okay, in the power form. Then next you can differentiate already. Easy, using power straight away. Straightforward. Bring the pi to the front times x to the power of pi minus 1. Okay. Okay, next. So what you encounter, a differentiation of two functions of x, and they are added together. So in this case, you just simply differentiate each term on its own. Okay, you differentiate this one plus, then differentiate this one. Okay, this is the rule, just like algebraic terms. And what if you have two functions, one minus from the other? Then you just differentiate each term separately on its own and with a minus sign there. Okay, and then what if you have a function that is multiplied by a constant? This is a constant. Any number constant. Could be 3, could be 20, or whatever, a constant, c, times a function. Then what you do when you differentiate, you keep the constant. Keep the constant. Don't go and differentiate a constant. Keep the constant as it is. Don't touch it. Okay, leave it as it is. You only differentiate the function. Okay. So example, y is equals to 3, x cubed. So 3 is a constant. Okay, don't go and differentiate a constant. When you do a dy dx, your differentiation, keep the 3 there. Keep the 3 there. Okay. You only differentiate the function using power rule. 3x squared. So it's equal to 9x squared. Okay, that's what it means here. All right. 3 is a constant. Don't do anything to constant. Leave it as it is. But of course, if you have y is equals to a constant 3. So what is dy dx? In this case, there's no x there. It's just a constant. So dy dx of a constant, as what I shown here, the first slide is a 0. When differentiate a constant is 0. Okay. Right. Next, more differentiation. Next. Okay. Go to next. You want to take a 5-minute rest? Shall we take a 5-minute rest? Take 5. Then we come back quickly
Okay.
to finish off. Okay, take 5. Okay, the rest of you can take 5. This is the last slide.
Thank
Okay.
you.
Okay. Take 5. Take 5. Come back soon. Go further back. Oops. Okay. Just like this one. Okay, you have two different functions of x and they are summed together. And when you differentiate them, you differentiate each term separately and still sum them. Okay. So we are applying this rule here. So find the derivative, means find dy dx. This is actually this y. Y is equals to 2x6 plus 3 root x using power rule. So dy dx. So you can say f prime x or dy dx. Same thing. Is equal to power rule. You bring the 6 to the front and it multiplies the 2 as well. So you get 12. X to the power of 6 minus 1 is 5. Okay. Plus 3 is a constant. Leave it there. And you differentiate root x. Root x. So when you differentiate root x, remember this is x to the power of half. X to the power of half. Okay. So you bring the half to the front is half. Okay. Times x to the power of half minus 1. Okay. So now you just clean it up nicely. 12x5 is 12x5. You've done it already. Plus 3 times half. So this is 3 over 2 already. Then x to the power of half. Half minus x to the power of minus half. So this is x to the power of minus half. So x to the power of minus half, you bring it down, becomes x to the power of half. Okay. So you just write it nicely. Do a bit of housekeeping. It's 3 over 2 square root of x. You want to leave it as is also okay. Like that also okay. It looks nice. Instead of leaving a x to the power minus half somewhere. Okay. Whatever way there, these two ticks as answer is okay. You see, using the power rule. Power rule. Still a power rule. See that? Power rule. Okay. Next is the application. We talk about acceleration. Differentiation can be applied to practical problem. Okay. First, we know what is acceleration. When a car accelerates, it increases its velocity over time. Okay. So acceleration is the instantaneous rate of change of the velocity. So, in other words, acceleration A, acceleration as a function of time, is simply the derivative of velocity. Derivative of v velocity. So the derivative velocity is dv dt. There. Derivative of velocity, dv dt. So in other words, if you differentiate velocity with respect to time, you get acceleration. So now differentiate velocity function with respect to time gives you the acceleration. Okay. WRT with respect to time give you acceleration. That's what it means. Okay. So we have example. Next slide. Example. Okay. Next slide. Okay. All right. Next. Go. All right. Example. Computing the acceleration. Suppose that the height of a skydiver t seconds after jumping from the airplane is given by this function of time. Okay, and it's in feet It's in feet. Okay, next time feet go a bit further. Oh, in feet not times feet It's in feet. Okay, FD is equal to 640 minus 20t minus 16t squared, and unit is in feet. Okay, so the height the height. So if an airplane, okay, airplane all right. So this is the height. Okay, that is, so he jumps, jumps. So this guy ever jumps. So 640. Okay, FT lah, FT. So this height is represented as FT. It's a function of T. So as he jumps down, okay, as he jumps down, he jumps, as he jumps down, okay, the height will change. As time goes on, the height will get less and less and less because it goes as he reaches the ground. Okay, with his parachute, across parachute, okay. So his height, so height is represented by this. So it's a function of time. Okay, it's minus. As time increases, the height get less and less. So what is the original height that he jumps? What height did he jump? What is this height? This height is 640 feet. 640 feet. Because when he starts, the time is 0. When time t is 0, when all the t's are 0, that gives you the original height that he jumps from, and that is 640. At starting time, start with t, time equal to 0, then you start, right? Then you jump, then t equal to 1, t equal to 2, t equal to 3, then the height get less and less and less. Okay, A, find the person's acceleration at time t. And B, all A's. B, and this is C. B, what is the height of the airplane when a skydiver jumps off the plane? So the height, we know 640. Answer already, B already answer already. When t equals 0, you put t equals 0 in the height equation, you get 640. So B already answer already. C is from the moment he jumps off the airplane, how long does it take before he hits the ground? If his parachute fail to deploy, poor fella, he will die. Okay, so if he jumps and his parachute fail to open, how long it takes before he hits the ground? Poor fella. Okay, so B already done. You put t equals 0 in the equation, you get 640. That's the original height that he jumps from. A is find the person's acceleration with respect to time. Okay, now enough space, so I use the visualizer. Advanced. Okay, visualizer. So we have this function ft, or y, we put y, height y, is 640 minus 20t minus 16t squared. Feet. Okay, so find the person's acceleration. So what you do is you differentiate this. This is a displacement. You can call it a displacement or height. When you differentiate a displacement, okay. Okay, give me a moment.
Yusof tayo.
Rabak, bro.
Give me a moment.
Alright, Sashi Darren.
What to do?
Okay, back to square one. All right. dy
Back to
dt.
visual.
So when you differentiate a displacement, you can say it's a displacement or height, if you like, displacement. Vertical displacement or height. So when you differentiate displacement, a displacement function, what would you get? Let's differentiate this. Power rule. You see, this is all differential power. Differentiate a constant is 0. Differentiate minus 20t, you get, what do you get? You get minus 20. So using power rule. Differentiate 16t squared, you get minus 36t using power rule. Power rule. So what's the unit here?
I think it's 32.
32. I say 32, right? But I write 36. So it's the speech and the thinking different. I say 32, right? I write 36. Okay. So what's the unit now? When you differentiate displacement, dy and divide by t becomes feet divided by t time second. So it's feet per second. Because displacement is in feet, then divide by time, the unit be feet per second. So it becomes what? Velocity. Okay, the velocity. Now you differentiate one more time. Okay, so this is your F prime D or this. Okay, so now you differentiate one more time, you get F double prime T, or if you like, it's your acceleration term lah. D squared Y over dt squared. Now differentiate as usual, power rule. Differentiate a constant is 0. Okay. Differentiate minus 32t is minus 32. Power rule. So this one, you divide by time again. So it's feet per second square. Okay. Feet per second square. So minus 32. So the acceleration, this acceleration, feet per second square is acceleration. So the person is accelerating at minus 32 feet per second square. So 32 feet per second square is actually your G. G is 32 feet per second square. Gravitational acceleration. Okay, G. This is your standard unit. In non-SI, G is 32 feet per second square. In SI unit, G is 9.81 meter per second square. This is non-SI. Now, so that is his acceleration. Downwards is represented by minus because the displacement, because upward is positive, downward is negative. So he is accelerating downward, show by minus, at a rate of 32 feet per second square. So it's 32 feet per second every second. So 32, then feet per second, then after that is another 32. So 64. So it's accelerating downward very fast. Very, very fast. Okay. So, yep.
Once you differentiate it the first time, right? So the dy over dt, that's supposed to be your velocity, correct?
Yep. Yep,
Okay.
correct. Okay. Feet per second is velocity or meter per second in SI unit. Okay. So that is velocity. Okay. This is velocity. This is displacement. This is acceleration. Feet per second square is acceleration. Okay. So, so his acceleration is 32 feet per second square downward lah. Show by negative sign. So acceleration is 32 feet per second square downwards. Show by the negative sign. So that's the full answer. For A. Yeah.
The unit for the acceleration is negative, right? So doesn't it mean that it's a deceleration?
No. The negative sign indicates direction.
Oh,
Mm.
all right.
Okay.
Thank you.
So it is positive acceleration. He's coming down. His velocity is increasing, not decreasing. And when you jump out of plane without parachute, your speed will increase as you approach the ground, faster and faster, and you hit the ground. That's it. That's the end, you see. It does not decrease. It increases. This is called acceleration. That's why it's called gravitational acceleration, not gravitational deceleration. No. G is gravitational acceleration. Okay, 32. This indicates direction, minus. Okay, so that's A. And B already solved already. 640. Put t equal to 0 in your displacement equation. You get the displacement. You get 64. Means at time t equal to 0 at the start when you jump, the height is 640 feet. Okay. Then what is C? C is from the moment he jumps off the airplane, how long does it take before his parachute fail to deploy? Poor fella. He won't stand a chance to survive, would it? Okay. So in this case, C, how would you answer C? How long would it take before it hits the ground if his parachute failed to open? Interesting question, isn't it? So in this case,
Prof, so
have
sorry,
to-
one more question.
yeah.
How gravitational acceleration is always constant at 9.8. How come it's
Okay.
different?
This is non-SI. SI unit is G is 9.81 meter per second square. Okay, you can convert feet per second square to meter per second square. You will get 9.81 meter per second square. You know how to convert, huh? First lesson in physics show you how the conversion is like already. Okay, so you
Right.
must know
Right.
some base reference. You must know a base reference rate or base conversion rate. A base conversion rate is 1 meter is about 3.28 feet. Okay, 1 meter is about 3.28 feet, or 3.28 feet is equals to 1 meter. Then you convert this to meter per second square lah. Your second square no change. Convert your feet to meter lah. Then you will get 32 feet per second square is equivalent to 9.81 meter per second square. Okay, we're dealing with non-SI unit here. Okay, that answers your question. Okay.
Yeah, okay, thank you.
Okay, right. Okay, so third one, C. So how long it takes before it hit the ground? If his parachute fails to open, poor fella, stands no chance. So how long? Means you find the time for him to hit the ground if his parachute fails to open. So in this case, go back to y is equals to 640. The given equation, given equation. That is the original. So again, y is the displacement, a vertical displacement, the height. So y is a function of time. This is a function of time. Okay, there, depend on time. When t varies, y will vary. Okay. So now, this is him, this is the ground. Okay, that is your y. It's given by this expression here. Okay. So your displacement starting from 640 feet become less and less and less, from 640 to 600 to 500 to 400 to 300 to 200 to 100 to 0 when it hit the ground, to 0. So to find how long it takes before it hit the ground, what will we do? You put this. When it hit the ground, his displacement is 0. His height is 0. When it hit the ground, the height is 0. Okay, 0 is equals 640 minus 20t minus 16t squared. All right, so now you solve this quadratic equation, solve for t, find t. Can solve or not? Okay, earlier, yesterday or whatever, or a day before, I've shown you how to solve a quadratic equation. You can use a bow tie method to factorize to find t. But in this case, you won't be able to solve for t using a bow tie method. So you got to use what? You got to use the formula. Okay. So t is equals to, because this is, okay, and then let me just put it this way. You can put it this way. Minus 16t squared minus 20t plus 640 equals 0. Then better, I can see better, right? So the coefficient of t squared is a. This is b. This is constant, this is c. Okay, this is the form a x squared plus bx plus c equals 0. So you use the formula. How to find x? X is equals to minus b plus minus square root of b squared minus 4ac over 2a. That is the formula to find x. Remember? Okay, I covered that. So use that formula lah. So instead of x, you have t. T equals to minus b. What is b? B is minus 20. So minus 20 plus minus square root of minus 20 squared minus 4 times a. A is minus 16 times c is 640 over 2a. A is minus 16. Okay, this I leave it to you, and you'll get your answer. T is equal to 5.73 seconds. So he hits the ground in 5.7 seconds. 5.73 seconds, he hit the ground. He'll be severely injured or he might be dead. We don't know, depend on the condition. Okay, all right. So you can do this and you find T is 5.73 seconds.
Sorry, Prof, what is the logic behind this? Like, I don't quite understand the concept of why we're just solving for t and how that is the answer.
Okay, all right. Now, y is the height. Y, which is a function of time, is the height. Okay, because engineers, you need to design. When you design, you need to do calculations. You need to deal with exponential function, logarithmic function. You need to differentiate and so on and so forth. Okay, so if a plane is flying up there and your commander says, engineer so and so, this plane up there, and he wants to know if one of his soldiers jump and his chute failed to open, how long it takes before it hit the ground. Your commander, your CO wants to know. Then you got to solve I solve for him. Okay, sir, I solve for you. Oh, 5.73 seconds, you'll hit the ground. Like CO will say, okay, I see. Maybe he just wants to know. Okay. And because he might think, okay, were his soldiers at the ground able to respond fast enough? But in 5.73 seconds, it's not possible. Not enough to respond fast enough. So we say, okay, plane fly higher, so that my men on the ground maybe can respond fast with a net or with something, so that the poor fellow will be injured but will not die. So commander may want to know, so you are an engineer in the SAF, you got to solve for him. Okay, so that's the logic, that's the application. So here, that is the displacement, the height. Okay, this is the equation involving how the height will change with increasing time. So as time increases, the height will less and less, become less and less, until eventually 0. And he'll jump now, he'll reach 0 in 5.73 seconds. Not fast enough for anybody on the ground to try to respond. To put a net or put a mattress there, not enough time. Okay, all right. So commanders like to see all possible scenario. They won't leave it to chance. You got engineer here and there. So engineer so and so. Lieutenant Tan, find out for me how long before it hits the ground. This if his chute fails to open. Okay, all right. I hope that answers your question. Everything has got important application.
Okay, thank you.
Right. Let's see screen. This one, is it?
Hi, Prof. Can I have a
Yeah.
question also?
Yeah.
So regarding that one equation that you showed, right? The
Yeah.
minus b plus minus, right?
Yeah.
How do you determine whether it's plus or minus?
How do you determine whether it's plus or minus?
One of it will be negative, then there's no such thing as negative time.
Okay.
Hmm?
Thank you.
Yeah. Correct. Yeah. No such. So you also learn to reject illogical solution. Okay, remember I done a rejection for you, one of the earlier calculation. Okay. All right. Always, time is always positive, can't have negative time. You cannot accept a negative. I can tell CEO, sir, he will hit the ground in minus 5.73 seconds. Minus 5 seconds? Your CEO will be scratching his head. Are you okay? Maybe you need to take MC. MC, go home and rest. Okay. All right. So now okay. This one wrong. Okay. Can you see my slide? Okay, good. All right. Next one is the product rule. We still have a bit of time. Just let me cover this 1 or 2 slides. Then we call it a day. Okay, this is another rule. We're done the power rule ready for differentiation. We're done already. Now we have the product rule. Product means product means multiply. We have 2 functions that are multiplied together. It means the product of 2 functions. Now you have to differentiate the product of these 2 functions. What is therefore the product rule? So when you differentiate this function and this function together, they are product. They are multiplied together, a product. Okay? Then you got to see, you see, in something like this, you may not have to apply product rule. You can go back to your power rule. Because you have x squared multiplied by x to the power of 5. Okay, use your earlier lesson 1, mathematics, your indices. You simply x squared times x5 is x to the power of 7. So when you differentiate x to the power of 7, use power rule. is 7x6. Answer, easy. Okay, so you have to observe, not every product of two function you need to use product rule. Sometimes you can use simple power rule. Okay, combined with other rules, you're involving indices, exponents, to get your answer easily. Okay, so note that when you have a product of two functions, x squared and 5 and x5, when you differentiate them, you don't separate them, and differentiate individual term. Wrong. You won't get the answer, because you separate like that, and then you differentiate each bracket accordingly. You get 10x to the power of 5, which is not the same answer as 7x to the power of 6. 7x to the power of 6 is your correct answer, and this is the wrong answer, you see. Okay, so be careful. Don't go and differentiate them individually, because they are product. Okay, don't go and differentiate them individually unless they are sum add together, 2x plus 5x4. Then you can differentiate them individually using the power rule. Okay, so don't make this kind of mistake. Okay, so here comes the product rule. This is the rule, product rule, involving differentiation. When you have two products, first a function of x, and next a different function of x, fx, gx. Okay, what you do is you first differentiate the first function, keep the second function unchanged, don't touch, just keep it there. Then you plus, then you keep the first function unchanged, you differentiate the second function. That's what it means here. Standing mathematics. Again, when you differentiate the product of two functions, here you have function of x and another one function, a different function of x. When you differentiate them, the rule says first you differentiate the first function, see, f prime x. Keep the second function unchanged. Don't do anything to it. Then you plus. Then you keep the first function unchanged. You differentiate the second function. That will give you your answer. That will give you your answer. Okay. Take for example, previously we used a power rule, right? Okay. Let's say, can we use product rule or not to do this? Okay, let's try. We have, oops, what happened? This thing comes back
Prof.
here.
Of your speed.
Okay, it comes back already. Yeah. Okay, can you see? You can see. Let's check. So, okay, y previously, y is equals to x squared times x to the power of 5. Right? So this is a fx and this is a gx, different functions of x. Previously, we used power rule, which should be the correct way to do it because it's simple function. But now we have learned the product rule. Can we use product rule or not? Okay. All right, let's try. dy dx. Now start to differentiate. So what's the product rule tell us? It says first, differentiate the first function, f prime x. So you differentiate the first function is x squared. So you differentiate x squared using, of course, product rule equal to 2x. Using power rule, you do 2x. Okay, differentiating the first function, x squared. Then it says keep the second function unchanged. Keep it unchanged. Then it's a plus sign. Okay, then keep the first function unchanged. First function is x squared. Then differentiate the second function. Second function is x to the power of 5. When you differentiate x to the power of 5, of course, you use power rule. Is 5x4. Okay, now you clean it up. You get 2x6 using the rule for indices or exponents. 2x6, okay, plus 5x6 using rules for exponents. So you are using rules and rules under this product rule. So you get 7x6. It's the same answer. Okay, same answer as if you just use power rule in your previous slide. Same answer. Right. Already time's up. Any questions so far? Any question? Looking at your chat box. Okay, you are chatting among yourself. Okay, all right. Unmute and answer and ask your questions. Okay, ask.
How do you know the password for the daily recordings?
Is there a password? I have no idea.
Yeah.
It's
and
all
it-
done automatically.
Mm.
Anyway, the recordings will not be released until after the course. I mentioned it before. Until immediately after the course. Then, okay. So not to worry, it'll be released after the course. Okay. All right. Any other questions? Those who have no questions, you may leave lah. Those who have no questions, you may leave. All right, for your lunch and come back 1:30 for your physics. Okay.
Can do
thank
the
you.
next example or not?
Next example, we'll do it together for the whole class. Instead of do for you, then I will do again the next morning. Okay, next example we'll leave to the next morning. No worry, no worries.
Okay, thank you, Prof.
Any other questions?